Good evening. Welcome to the next video in our Let's Calc series. In this one we're going to step forward into the third unit of the course, which focuses on analysis. In this lesson and in this problem set video or video solutions video, we're going to be looking at all the implications of the Extreme Value Theorem, how to find both critical numbers and extrema, how to use the candidates test, as well as some other interesting and analysis-based tools. Without further ado, let's jump into the first problem. Okay, the first question we are going to attack is question number 2 from the first section of the assignment. In the instructions there for number 2, we are directed to find the critical numbers for each function and to show all work leading to our answer. So it's an important thing to note first what the definition of critical numbers is, especially for me because I've used an incorrect critical numbers definition in the past, which just kind of causes some ambiguity sometimes. So a critical number is going to be a value x equals c such that, so in other words, a critical number would be an x value. We're looking for a particular x value where a certain property holds. In particular for a function f of x, so in fact I should have said a critical number of f of x, and it would be an x value x equals c such that f of c exists, first and foremost, and f prime of c equals 0 or is undefined. So and the reason I bring this up first to start is we have to be careful because although there are lots of values that are really important, particularly when we start using the first derivative test and start making sign charts for the first time, the important thing to note is that there are numbers that are not critical, where f of c does not exist, but there are places that are nonetheless important. So we'll talk about some of those situations for now. For the moment, this is what we need to use as our definition, is we're looking for x values where the function exists and the derivative is either 0 or undefined. So that could just mean that the function is not differentiable there due to a sharp turn. It could be something else entirely, like a vertical tangent, just kind of depends. So to start off here, let's take a look at what we've got. So sine squared minus root 3 cosine of t. By the way, a nice point to point out is that sine and cosine functions, sine and cosine functions are perfectly continuous, so are any algebraic combination of the functions. So this is definitely going to be a continuous function, so we don't have to worry about any non-existent derivative values. And I will also note that we are being asked to find the values on the interval from 0 to 2 pi. So we're just focusing on one revolution around the unit circle. So in particular, for us to get going, the important thing to note is that we're talking about places where the derivative is either 0 or undefined. So for our purposes, what we need to calculate is g prime of t. So in order to do that, we need to differentiate sine of squared of t minus root 3 cosine of t. So in here, you can imagine for a second, being super careful in our first example, we've got to take the derivative of sine of t squared minus root 3 cosine of t. And while I don't want to spend forever doing all the derivative parts of these kinds of problems, because there will be plenty, I will point out here that this is going to be the most difficult portion of this particular derivative. If we want to do the derivative of sine of t squared, we might look at this as the outside and the inside. The derivative of the outside is 2u, the derivative of the inside is cosine of t, which gives us the derivative we'd be looking for, 2u u prime. In our case, that would be 2 sine of t cosine of t. So in bringing over here, if we want to calculate out our derivative, we can do that now that we found that derivative of sine squared. G prime of t is going to be equal to 2 sine of t cosine of t. And then over here we've got the derivative of minus root 3 cosine of t. That's become minus a negative root 3 sine of t. So there is the derivative. That is the most important first step of finding a critical number, is we've got to have an accurate derivative. Now that we do it though, our job here is to figure out where this function, aka the derivative, is either 0 or undefined. Now we mentioned earlier, because of the continuity of sine and cosine as well as the differentiability, this combination is definitely going to be differentiable, so we're only looking for zeros basically. But this isn't a trivial problem to solve. So here's what I'm going to do. First thing I notice is that there's a GCF of sine, so I'm going to factor out a sine of t. You're getting some advanced trigonometric solving here. So we need to solve this equation. Of course, with the zero products property, we get two options. We either can have sine of t equals 0, or we can have 2 cosine of t plus root 3 equals 0. Those are our two options. Well, if sine of t equals 0, we're talking t as 0, pi, or 2 pi. But remember, we did say we were on the open interval from 0 to 2 pi, so really the 0 and 2 pi are out. Our only possibility from that factor will be t equals pi. It's nice. On the other hand, the second one will give us our t values, our critical values, when cosine of t equals negative root 3 over 2. And if we draw a quick little picture here to think about it, cosine is negative in quadrants 2 and 3. We're looking for cosines, the adjacent, to be negative root 3 over 2. That means we're opposite of 1 with our reference angle. That means this is a 30 degree or pi over 6 reference angle. And in quadrants 2 and 3, the relevant radians are 5 pi over 6 and 7 pi over 6. And given that information, we're asked to just find the critical numbers, not the critical points. So we don't need to actually calculate their y values here. But the critical numbers for our particular function, g of a t, are going to be t equals 5 pi over 6, pi, and 7 pi over 6. And if you're wondering why I wrote them in that order, it's simply for numerical value. So turns out there are 3 critical values. So remember, these aren't necessarily maxes or mins, but they are potential maxima and minima, potential extrema. So there it is. Again, derivative equal to 0 or undefined. Solve the equation, find your critical numbers. Okay, our next example we're going to look at is the same instruction, same set of problems. We're still looking for the critical numbers of each function, and we want to show our work. But in this case, we're given a product of binomial powers. And in this particular problem, I'm not going to go through and do the full derivative carefully. I'm going to expect you to be able to keep up with the quicker version of the derivative. So naturally, as we mentioned before, what we want is y prime to be equal to 0 or undefined, as well as y exist. So we need the function to exist at each critical number, and we also need to find, whether 0 or undefined. So in looking in here, first and foremost, we need to calculate the derivative. So I will be kind here a little bit. We need to use the product rule first. This will be the derivative of 2x plus 1 to the 7th times 3x plus 4 to the negative 3rd. Then it'll be plus 2x plus 1 to the 7th times the derivative of 3x plus 4 to the negative 3rd. So there's our function that we want to do. We want to do this derivative. So working through each piece here, derivative here is going to be 7 times 2x plus 1 to the 6th times the derivative of the inside. And since that inside is the line 2x plus 1, the inside derivative is going to be 2. Then we'll have 3x plus 4 to the negative 3rd. On the next one, we've got the 2x plus 1 to the 7th to deal with. Next, we're going to bring down the negative 3x plus 4 to the negative 4 times the derivative of the inside. Once again, we have a line. Derivative of the inside is just the slope, or 3. So cleaning this up just a little bit, we're going to get 14, 2x plus 1 to the 6th, 3x plus 4 to the negative 3rd. And then over here, we're going to have minus 9, 3x plus 4 to the negative 4th, 2x plus 1 to the 7th. So with this in place, our next job is to factor out a GCF so we can see what the remaining factor is. So looking first numerically, actually we'll do GCF right over here. Actually, I'll do it in a different color, what the heck. We've got all the colors at our disposal. Okay, so looking first at numeric GCF, we ask ourselves, do 9 and 14 have any factor in common? Beyond 1, no. So basically those ones are safe. Next we look at 2x plus 1s. We want the smaller power every single time. That's going to be 2x plus 1 to the 6th. And then finally, we've got 3x plus 4 to the negative 3 and negative 4. We want the smaller power, which in our case is going to be to the negative 4. So there's our GCF. That means we can pull it out in front. In fact, we can pull it out in front so much, we can literally cheat the process, I think. Look at this cleverness. Boom. Go back to my other color. Okay, so there's our GCF. We have to look at what's left over now. Well, we pulled out 6 2x plus 1s. We still have the 14, and we'll end up with 3x plus 4 left over. Then we'll have the minus 9. And of course, we pulled out 6 2x plus 1s, so a single one remains as well. Now, focusing on that last little part here, we're going to get 42x, yay, plus 56 minus 18x minus 9. And if we want to write the entire thing together, we'll just pull the GCF down. we're going to then have as our remaining factor 42 minus 18 is, I believe, 24. So 24x. 56 minus 9 is positive 47. So that's a lot of work. I know it's tempting to go, yeah, I'm done. But remember, that wasn't the question we were asked. We were tasked, let me remind you, my friends, to find the critical numbers for each function. So we're looking for where the derivative is 0 or undefined, as well as when y still exists. So looking in here, it's very tempting to write out, right off the bat, that the critical numbers are just the 3 zeros that we see there. We get x equals negative 1/2, negative 4/3, and negative 47 over 24. And what a fun collection that is. Unfortunately, this would be wrong. The reason is a little bit subtle here. 2 of these are critical numbers. The other one is not. The other one's what we just call an important value to consider later. So let's look at this for a second. This expression, I mean, everything's pretty good, except we've got that negative 4 power up there. What that means is there's an alternate way you could write this function, or this derivative of the function. You could write this instead as 2x plus 1 to the 6th times 24x plus 47, all divided by 3x plus 4 to the 4th. Now, why is that relevant? Well, if x equals negative 4/3, y prime does not exist. So at first you might say, okay, well that's fine, y prime doesn't exist. We said it could be undefined, but here's the problem. If you go into your original function and put negative 4/3 in, you'll end up with 0 to the negative 3rd power, which would absolutely lead to a number over 0, which means y is not defined. Or let's just say it this way. Y does not exist at x equals negative 4/3. So in fact, we do not have a critical number right there. Our only critical numbers, the only ones that are going to insult you, even if they're trying to make you feel better, or even if they're trying to make you better, it didn't work. Ignore that. The only 2 critical numbers are negative 47 over 24 and negative 1/2. So there is the solution. This is our first one where we had a distractor critical number to look out for. Keep that in mind. A vertical asymptote, the vertical asymptote, or the x value where a vertical asymptote occurs, is very important, but it does not qualify as a critical number by definition. So keep that in your mind. It's a new thing for me too, but I think we're going to get it in hand. Okay, question number 6 is our next point of attack. And this moves us away from just simply finding critical numbers to starting to look at expressions themselves. So in 6, we are instructed to find the absolute extrema of g of x equals that polynomial on 0 to 3. And we're supposed to show all of the work that leads to our answers. So keep in mind here as we start to work, and I'm just shifting my stuff to make sure I don't do any bad arithmetic here. Don't want to mess that up. As we go in here, the important thing to know is when you're asked to find the absolute extrema, what that's code for is to use critical numbers and the candidates test. That's how we locate absolute extrema. We find all the places where an extremum might occur, then we combine those places, or we check the y values of those places, and we literally compare their relative sizes to find the biggest and the smallest ones respectively. And when it says show all your work or justify your answer, the candidates test is, amazingly, that work. Like all the work leading up to a properly done executed candidates test is the work that you do to show that you found the correct absolute max or min. So in our particular case, a good place to begin is to focus on the derivative. Of course, the derivative is relevant because we're talking about critical numbers, and absolute or extrema can occur at critical numbers. So in looking up here, we have the derivative of 8x cubed, just 24x squared, minus 18x, minus 60. If we factor this puppy up a little bit, I think we can pull out a 6. Yeah. So 4x squared minus 3x minus 10. So if we're looking for numbers to break this apart, we got to have numbers multiplied to negative 40 add up to negative 3. Pretty sure that's going to be 4x squared minus 8x plus 5x minus 10. Let's see if this works. I think it does. So factoring a little bit further, I'm just going to write it right here. We're going to have 6 quantity. That's going to be 4x plus 5 times x minus 2. You can do a quick multiplication out if you don't trust that works, but I'm pretty sure it does. Now that we found g prime, and of course we've recognized that we have a polynomial, meaning that the function is continuous and differentiable everywhere, that means that all we have to do is set this derivative equal to 0. And when we do, we find our critical numbers. Looks like there are going to be two of them. There's a critical number at -5/4, and there's a critical number at 2. And I forgot to write x equals, of course I did, and I'm going to have to rewrite it. Gosh, the world's helpful sometimes. Okay, so there are critical numbers. So now, we found all our candidates. In fact, as we think about this, we can realize that there are only 4 possible candidates here. Our candidates always include 2 types of values. We can either have them at critical numbers or endpoints. So the only x values we need to choose are the ones that are in our interval as well as the endpoints. So in looking, since we're on the interval 0 to 3, what that tells me is that -5/4 is out. Unfortunately, a negative number is outside the interval from 0 to 3, so we don't even need to check that. It's no longer a candidate. It's like it's a great, if we're talking about the political analogy here, it's like it's a great candidate, but it's not eligible to run for president. Maybe it's 34 or something, or who knows. So unfortunately, we can't consider that candidate at all. It's just not where we're looking at this time. So instead, we're going to use our 3 candidates, 2, 0, and 3. So in looking here, we can set up a candidates test table, and this is actually the accepted way to do this problem. Don't feel like this is some sort of cheat. It's just a really quick and very easy to compute technique. So we're looking to use the candidates test. We're going to compare x values to our function values, which come from 8x cubed minus 9x squared minus 60x plus 1. And I'm spending the time doing this very basic problem to remind you about some important stuff, including this. A lot of people mess up by choosing, instead of g of x to use in the candidates test table, they accidentally use g prime of x. Remember, what we're trying to do in the candidates test is, now that we've found the potential ones that could have our max or min, we want to compare and see which one's biggest and which is smallest. It's kind of like looking at 2 mountains next to each other and going which one's taller, or which one's shorter, depending on your perspective. So that's exactly what we're trying to do here. So we are going to plug it into g of x, the original one, to get the original correct y values themselves. So let's take a look here. So our 3 candidates, we mentioned, they were 0, 2, and 3. And I don't want to spend forever doing all these calculations, but at least for 0 it's easy. G of 0 is literally going to be 0 plus 1 is 1. So now having one value tells us nothing. This could be the max, this could be the min, this could be the middleist. Like the middleum, that's not a word, but it could be. Let's look at 2 instead. This is going to be 8 times 8, because 2 to the third is 8, minus 9 times 4, minus 120, plus 1. That's 64 minus 36, which is, I believe, 28, minus 120 plus 1 is going to be our value. And again, making sure that I just get the right numbers here because I don't want to spend forever on it, we get -91 as our value. I think that makes sense. 29, 30 minus that would be -90. You have one more there. So voila. So now at this point, we know for sure that 1 is not going to be the minimum because -91 is smaller. But we still don't know anything else. So to find the last one, we need to check at 3. It's going to be 8 times 27 minus 9 times 9. Oh, sorry. Minus 180 plus 1. So once again, pulling out all the correct values here. I'm just going to speed through the arithmetic. That's why I wrote down those numbers. This comes out to be -44. So from here, to make our decision on what our extrema look like, we look for the biggest and the smallest. Clearly the smallest is going to be -91. That's our smallest y value, which means that the absolute minimum occurs there. And the largest, weirdly enough, or the biggest, ends up being at literally y equals 1, or g of x equals 1. It's kind of crazy. So now that brings us to the final part of the problem, which is to state the correct answer. So we were asked to find the absolute extrema. So we want to find the absolute maximum, and we want to find the absolute minimum. The way we present these answers, though, can sometimes get to people. So the way the question's asked, and I believe with the 3 questions you see, you get 3 different ways of asking. To make this determination, we need to state them based on the correct form. So if you're asked for purely the absolute extrema, what you're likely looking for is a point x comma y. If you're asked for the x coordinate of the absolute maximum or something, then you're asked for the x coordinate, obviously. And if you're asked for the maximum value or minimum value, then they only want the y value. So in our case, because it's the literal full phrase, absolute or global maximum, absolute or global minimum, we want the ordered pair. So for absolute maximum, that would be the biggest, which was 0, 1, and the absolute minimum would be the smallest, which was 2, negative 91. And there is the answer. And again, we showed all our work, obviously, but also if they'd asked us to quote-unquote justify our answer, our justification would literally be this and this combined. That's proof. That is our work for the candidates test. That's how you know you're doing it correctly. So again, pretty straightforward instance of the candidates test, but I think still a good one to illustrate and kind of show you the ropes of this new technique. Okay, that brings us to question number 8. Question number 8 is a great wrinkle-filled problem. So in question number 8, same style as the previous one we just did, we are asked to determine the maximum and minimum values. So I'm going to underline that first. What they want is y equals in this case. So they're not looking for the ordered pair in this case, they want y values. They want function values. Next, they tell us our function. It's a pretty crunchy one, an interesting one, a little bit of spice on there. 3t to the 2/3 power minus t plus 10. And then finally, we have t as a member of 1 to 27. So in order to get here, of course, an important first place to look is going to be to determine the critical values, critical numbers. So we want f prime of t in this case. We're going to take the derivative of these pieces. Well, the first one is going to be 3 times 2/3 t to the negative 1/3 minus 1 plus 0. That means our derivative is going to be 2t to the negative 1/3 minus 1. And of course, I see that 1/3 and the minus sign, so I'm just going to rewrite this a little bit. I'm going to rewrite this as 2 over the cube root of t minus 1. So there is our derivative. So now, before we get into anything big and we start setting things equal to 0 to find those critical numbers, I'm going to point out that right now we have something interesting. At t equals 0, it would seem that we have some sort of asymptote, right? F prime of 0 does not exist. But here's the thing. If you plug 0 into our original function, 3 times 0 to the 2/3 is 0, minus 0 plus 10, f of 0 still exists. What that tells me is that our first critical number is t equals 0. So this is a slightly different situation than our asymptote earlier. In asymptote, there's no function value. In this case, the asymptote we get on the derivative is due to what is a vertical tangent. Turns out 3t to the 2/3 power actually produces a vertical tangent, which is interesting for sure. Oh, excuse me. Okay, so we found t equals 0 is a critical number. That's important, but we haven't found the rest. So to find the other, we need to know when does 2 over cube root of t minus 1 equal 0. Well, solving this equation around, we get 2 over cube root of t. Cube root of t equals 1. That's going to mean 2 equals the cube root of t. And then I think it's simple enough to just cube both sides at this point, and we get 8 equals t. So we have two critical numbers here. One came from an undefined slope. So at x equals 0, we have a critical, or sorry, not x, excuse me. We're using t here. At t equals 0, there's a critical number where the slope is undefined, but obviously f exists. And we also have one at t equals 8. And notice both of those, oh, look at that, interesting. T equals 0 is not in our interval. Darn. Actually, I'm kind of disappointed. To be fair, I really had hoped we'd be able to use it. But whatever. We have a critical number. We only have one that we need to look at. But this is now enough for us to go through the candidates test. In fact, all of the work was just to talk about that t value. So, oh well, here we go. So, candidates. Let's grill some candidates. Set up the debate. So this is going to be t versus f of t, which is 3t to the 2/3 minus t plus 10. So looking at values, the first one we have is at 1. If we plug in 1, we get 3 times 1 to the 2/3, which is 1, minus 1 plus 10. That's equal to 12. So nothing too crazy, but easy to do. Second value we want to plug in is going to be the middle, 8. if we do 3 times 8 to the 2/3 minus 8 plus 10, 8 to the 2/3 is 64 to the 1/3, which is 4. So this is equal to 12 plus 2, which is 14. So we have a new candidate in the house for absolute maximum. Finally, we have 27. It's going to be 3 times 27 to the 2/3 minus 27 plus 10. Looking at values, 27 to the 2/3 is the same thing as 27 to the 1/3. Here, I'll do this off to the side just in case these things give people trouble. 27 to the 2/3 is the same thing as 27 to the 1/3 squared, which is the same thing as 3 squared, which is 9. So this becomes 3 times 9, or 27, minus 27 plus 10 equals 10. So with that in place, we now know our smallest. In fact, I'll do this with red again. I thought that was cool last time. Our smallest turns out to be the right endpoint, interestingly enough. And our biggest turns out to be the critical number. So with that in mind, again, communication is very important here. We wanted maximum minimum values. So to do that, we can write first that our max value is the biggest y value, which is 14. And our minimum value is going to be the smallest of the y values. I want to say it was 10. Yes, it was 10. Voila. There is our work. Notice in question number 8, there was a little bit more to do here. We had to be a little more conscious of the definition and potentially include a critical number that occurs at a place where the derivative was undefined. For the most part, everything else worked out really nicely. And we have our answer to question 8. Okay, next we move on to question number 9. Question number 9, one of my favorite types of questions out there, is the table-based function, the numerically presented function. And as it says in our instructions for 9, the table at right gives values of differentiable function t and its derivative, which is t prime of x. 9a then asks us to find the critical numbers of t of x. So in this case, since we have a differentiable function t, that means t prime is continuous. It does also mean t is continuous, but I'm getting ahead of myself a little bit. So if t prime is continuous, we don't have to worry about any place where t prime does not exist. That means we're looking for here all of the places where t prime of x equals 0. So we want t prime to equal 0. I see 1, 2 values. So with that in mind, it looks like we're going to have critical numbers of x equals -2 and x equals 5. So nothing super involved to attack in question 9a, but it is important to be aware of how to approach this question when it's presented numerically, for sure. But again, we only have 2 critical numbers, -2 and 5. Question B then asks us to find the global extrema of t of x. So global of extrema sounds like we're looking for the absolute max and absolute minimum, just another word for it. And our interval is from -6 to 11. So what I'll remind you is that we have 2 different ways to have candidates for this particular position of global extrema, or absolute max and absolute min. Our candidates are all the critical numbers and both endpoints. Those are the 4 candidates we need to consider here. Based on our previous problem, we said there were 2 critical numbers. There was x equals -2 and x equals 5, and our endpoints are clearly -6 and 11. So as weird as it is, when we don't know anything else about the function but a table, we are actually in position to now use the candidates test. So this one should be pretty simple. We're using t of x. We're trying to find the largest and smallest values of t of x. Our candidates are -6, -2, 5, and 11. And then our values themselves, t of -6 is 5. Again, we don't know anything yet. T of -2 is -2. Okay, we have a new minimum candidate. T of 5 is -4. Aha! The minimum has been usurped. And then finally, t of 11 is going to be 7. So in grand candidates test tradition, we're looking for the biggest and the smallest of these. The smallest is going to be at t equals 5, or x equals 5, sorry. And our biggest is going to be at the right endpoint. So from here, global extrema, we want the global maximum. So the global maximum is going to be at the point 11, 7. Again, notice I'm using the x and y coordinates. like they didn't ask for the value or the x-coordinate alone, so we include both. Then second, we'll look at the global minimum. In other words, the point at which the smallest y value is attained. Looking at our picture, the smallest one occurs at x equals 5, which is -4. Excuse me. So there are our global extrema, the global max at 11.7, and the global minimum at 5, -4. So in here, what was really important was using that information about that definition of critical numbers to find the information from the table that we needed, as well as looking at the endpoints and reading properly from a table. Okay, this next question brings us to question 9C. It says next, ooh, I love this question. This is one of my favorite ones that I wrote. It is known that t prime of 14 equals -2. We're looking over at our table. Whoever made the table did not have time for that, so they didn't even make that. But now we know. T prime of 14 is -2. Then it says to prove that t of x has a critical number, x equals c, with 11 less than c less than 14. So we're trying to prove that t of x has a critical number. So in other words, we're talking about values of, we want to show t prime of c equals 0. So keep that in the back of your mind. So in here, it's going to feel a little bit weird, but we're trying to show that there's a particular value of the derivative given a value of the derivative. So here's my thought. I'm thinking this actually feels like a really different version of the intermediate value theorem. So bear with me for a second. Intermediate value theorem requires two properties. Can you say those two properties off the top of your head? Continuity and boundedness. I think I heard you through cyberspace and a time machine, apparently. But that is correct, strange, confused voice. Continuity and boundedness are the two things that we're looking for. Is our function going to exist everywhere in between the two endpoints? And do those endpoints bound the value we're looking for? Those two properties we'll verify the intermediate value theorem applies, and we'll be able to draw conclusions from there. So let's think first. So, is t prime continuous? Because that's what we'd need in this case to start to make guarantees using the intermediate value theorem. Well, what did they tell us? They tell us that we have a differentiable function t. T is differentiable. So in other words, we have a guarantee from there, because t being differentiable means t prime is continuous. That is the definition of differentiable. That is one of the properties that is said there. So that part's good. So we do have continuity. Nice job, us. We'll restate it properly in a second. The second question is t prime of c equals 0 bounded? Well, let's look at our contenders. We're interested in the interval from 11 to 14. Actually, I'll do this in a different color. So we're interested in the interval from 11 to 14. Looking in here, t prime of 14 is -2. They told us that. What about t prime of 11? We're trying to show t prime 0, so we probably want a positive number here. T prime of 11 is equal to 5. That's a good sign. That means that 0, the value we need to be a critical number, is bounded as well. So this means that the intermediate value theorem absolutely does in fact apply. So that means we can set up our statement, or we can set up our proof, in fact. It does ask us to prove it. So in our proof, we want to make some statements. So we need to guarantee both properties are there and state them as nicely as possible. So first of all, t is differentiable so thus t prime of x is continuous. And, based on the kind of following along the same things we can do, and we have that t prime of 14 is less than 0 is less than t prime of 11. And again, we don't need to say more than that. We don't need to state the values because we already established them right up here. So as long as we did that good work ahead of time, we're covered. Thus, since we've just shown that t prime is continuous and 0 is between them, thus, by the intermediate value theorem, which I'm going to write out here, just because good habit to get in. You can always skip ahead a few seconds to finish this off. You never know, you can miss a joke. Thus, by the intermediate value theorem, t prime, let's go this way, t prime of c equals 0 for some value. Let's see what we have. 11 less than c less than 14. So you would think we were done, right? Because that's basically the general statement of the intermediate value theorem. But we were asked to prove that t is a critical number. We haven't mentioned critical numbers. So to finish this off, and note that critical number portion, I'll even pull in a different red here to finish this off. So to finish this, and by definition, there's your abbreviation of definition, if t prime of c equals 0, then c is a critical number of t of x. Done. So there's our proof. We used all that we had kind of learned. We used the intermediate value theorem to bound things. We were able to show that in between there had to be a 0, which was by definition a critical number. We were able to finish the problem off nicely. So really interesting problem to think about, kind of call back to some stuff, but also really powerful move forward with our new tools. Okay, finally that brings us to 9D. 9D does not have anything to do with the analysis we've been doing. It's just a really nice throwback to the chain rule, which is such an essential skill. Oh look, let c of x, maybe c for chain rule, equal t of negative t of x. Our job is to compute c prime of 1. So I've already mentioned to you that I'm thinking chain rule. Chain. So there's where our thought is. So let's break this up. I'll be careful in these first couple videos. C of u is going to be t of u, and then second, u, the inside function, is going to be negative t of x. Right, all we've done is decompose the function. Next we differentiate each piece. We're going to have t prime of u, and then u prime is going to be negative t prime of x. Bringing those pieces together, we're going to get t prime of u times negative t prime of x. But of course we can plug back in for u, and we'll get that our answer is negative t prime of t of x, negative t of x, times t prime, there it is, times t prime of x. Already had the negative in front. So there is c prime of x. Our question, though, wasn't asking us about c prime of x, but specifically c prime of 1. So to do that, we need to substitute. We'll have negative t prime of negative t of 1 times t prime of 1. Pulling some values out here, we're focused on this portion right here. For the moment, we're going to get negative t prime of negative t of 1. Well, t of 1 is 6, so negative 6, times t prime of 1, which it says right here, is negative 6. Finally, simplifying this a little bit, we got negative something times negative 6 is positive 6 t prime of negative 6. To finish this off, we need t prime of negative 6, which turns out is 4. So we're going to get 6 times 4 is 24. And there we have our value of the derivative of c at x equals 1. So a challenging problem a little bit using the chain rule. Really easy to drop those negative signs. I swear when I did the written solutions as well as here, I've been tempted to do it each time. We get to our answer fairly smoothly just using the chain rule. Okay, that brings us to our next question, which is the final part of question number 9. That is question 9e. In this case, once again, not really connected to the analysis, but an important thing to be able to do nonetheless. We're told that q of x is equal to x squared over t of 2x, and we're asked to write the equation of the tangent line at x equals negative 3. So to start off here, I'm just going to jump into the first thing that hits my mind. I want to figure out what the y value is there first. Otherwise, it's easy to forget as you're doing the differentiation. So that's going to be equal to negative 3 squared over t of 2 times negative 3, which is going to be 9 over t of negative 6. Looking at our value, t of negative 6 is 5. That means our y value is 9/5. So that means up here in our tangent line, when we go finish this problem, I can set it up as though we're ready, we get y minus 9/5 is equal to something x minus a negative 3. So all that's left for us is, of course, figuring out what the slope is. So let's do that. Let's find q prime. So to get q prime of x, of course, looking at our function, we've got a function over another one. My thought is we're going to use the quotient rule. But of course, let me remind you really fast that the quotient rule doesn't mean that you can't necessarily use another rule. And in fact, that denominator, complete with that 2x there, that's going to require us to use the chain rule as well. So we're going to get a little bit of a chain in there just as well. Okay, and looking here, first, again, being really careful in the first assignment of this new chapter, we've got low d high, the derivative of x squared is 2x, minus high d low. This one might take a little bit of work, so I'm just going to leave a chunk there for it. All over low quotient rule. So there's my stuff. You can see that the one place where I paused, though, was in computing the derivative of t of 2x. And the reason is, of course, this requires the chain rule. And I said for at least the first couple assignments here, I was going to be really careful and demonstrative doing the derivative, or the chain rule and derivative work. So in here, let's be super careful. Let's let there be f of x, which is equal to t of 2x. This is one where I would hope that you could get through it faster than this, but still, we'll play along. We'll let u be equal to 2x. We'll let f of u be the outside, which is t of u. Have f prime of u as t prime of u, and u prime is equal to 2. So without further ado, bringing this back, we're going to get f prime of x is 2 t prime of u. So in fact, for the sake of argument, I did the work over there. If you want to see it, you can. I'm going to just go ahead and replace this as 2 t prime of 2x. So with that in mind, our derivative now reads, actually I'll go back to the right color. So this now reads 2x t of 2x minus 2x squared t prime of 2x, all divided by t of 2x squared. So there's our derivative. Of course, that is q prime of x. We're interested, though, in what happens specifically at -3. So to wrap this puppy up, we want to calculate q prime of -3. Simplifying this as quickly as possible, it's going to be -6 t of -6 minus 2 times -3 squared is minus 18 t prime of -6 all over t of -6 squared. So pulling out values as much as we can, t of -6, we're focused in this column here, by the way. T of -6 is 5, so that's -30. T prime of -6 is 4, so that's going to be minus 18 times 4, which is minus 72. And all of this is over t of -6, or 5 squared, which is 25. That simplifies to -102 over 25. And with that in place, in our tangent line equation up here at the top, there is the tangent line in question. So again, a little bit of quotient rule, a little bit of chain rule, and some tangent line work, but otherwise a pretty straightforward and quality problem for us to wrap up question 9 with. Okay, that brings us then to question number 10. Find the x values guaranteed by the extreme value theorem for f of x equals 2x plus 5 and 2 less than x less than 16. So I decided to throw this question in after finishing the entire solutions for the assignment, and you'll be able to see proof of that when you do the problem sets, or if you look at the written solutions to this problem set. But I thought it was an important one to put in there, even just to get that phrase extreme value theorem onto the assignment, because of course first we already know the intermediate value theorem, and likely tomorrow we're going to hit a second value theorem. But more than that, what I wanted to bring up was the idea that the extreme value theorem guarantees us the existence of particular x values too. So what does it mean to find those values, or to apply the extreme value theorem? So let's start by reminding you what the extreme value theorem, well, since it's written up there, I'm just going to write it as the EVT. It sounds like the kind of drink that super evolving Pokemon would drink if it's into caffeine. EVT, whatever. So in this case, EVT, what that says is it says that all continuous functions this may not be a word-for-word definition, but it's the exact idea. All continuous functions have a maximum. Actually, I don't think I need the word a. All continuous functions implies plurality, so I'll just put it in there. Have maximum and minimum values on a closed interval. So basically what they're saying is if you have a continuous function and it's being analyzed on a closed interval, there is guaranteed to be an absolute maximum and an absolute minimum. Now they might not be unique because of course a constant function, the maximum and minimum values are the same. It's the only function value that's attained. But the idea here is that you can find them through using other techniques, but you're guaranteed to have a place where the max and min occur. So this one is, again, a very strange question, but I thought that it would really hit the topic in a straightforward way while making the computations really easy to work with. So let's take a look. So we're interested in using the extreme value theorem with f of x equals 2x plus 5. So first of all, to point out, we need continuity. Continuity is a guarantee or is a requirement of this particular theorem. So basically the function is 2x plus 5. This is a polynomial. Yes, we'd probably call it a line or a linear function, but polynomial is a broader group of, structure or broader structure. So it's a polynomial, which implies that f of x is continuous. So that's our first bet. We need to make sure that we can actually apply it. So good for us, we do. Next, we're on the closed interval from 2 to 16, so there's nothing we have to really worry about there to show. Obviously, we have a closed interval. What we do want to do, though, is find where the extreme values might actually occur. And we know that either occurs at the endpoints or critical numbers. So let's see for a second first, what are the critical numbers? So the derivative of 2x plus 5 is 2. Unfortunately, 2 never equals 0, which means there are no critical numbers. Now again, pause, hold that gasp for just a second. Yes, there are no critical numbers at all for this function. It has no critical number whatsoever. But that's not a problem, because as we said, the candidates for where these extreme values might occur are the critical numbers and the endpoints. So just because there's no critical numbers doesn't mean we don't have any candidates for the high or low points. In this case, those candidates are the two endpoints 2 and 16. From there, we can find our maximum and minimum values by plugging them in. Of course, 2 times 2 plus 5 is 9. And f of 16, I believe I made this as an homage to good old mighty Chen, but let's see. It's going to be 32 plus 5 is 37. I did. So we have our small value, and we have our big value. But more importantly, the question we were asked was, what are the x values guaranteed by the extreme value theorem? As in, what are those points? Where are those x values where the maximum and minimum will occur? That means that the values we are guaranteed, EVT guarantees, in our case, x equals 2 and 16. So again, it's a weird question, even with such a simple thing to look at, but you can tell there's some interesting wrinkles in here. We had no critical numbers, but that wasn't a problem. We're asking you about x values guaranteed by the extreme value theorem. Definitely a little bit weird, but I'm hoping this is just the first opportunity for you to realize and think about once more what that extreme value theorem itself says. If you've got a continuous function and it's on a closed interval, there will be a maximum and there will be a minimum somewhere in that interval. So, voila, 10 is in the books. Okay, next, that brings us to 11. Gosh darn it, I'm ready to be done. So in question number 11, it says, consider the function w of x graphed at right. And that's quite a function. It says, find the x-coordinates of the absolute maxima and absolute minima, respectively, for w of x on each interval, with no justification or candidates test needed. So in a sense, what we're looking for here is we just want to know where is the absolute max and where is the absolute min. And for the sake of time saving, I'm going to literally copy this and paste it into each section here. I don't want to keep, this isn't my favorite question of the assignment. I think it's just a good one to look at. So, boom. Okay, so let's take a look. So our first interval, a to d closed interval. So now first of all, things to think about. If function w, and of course this is w of x, if w is continuous, then we'd be guaranteed on this closed interval to have an absolute maximum and absolute minimum. Unfortunately, no. It's not a thing that we have. So we aren't guaranteed one here. So keep that in mind, that because this function isn't continuous, we may not be guaranteed to have a particular value. Looking at our stuff, though, it's important to figure out where the big and small values happen to be. So first, it looks like the biggest value occurs right there. It's like at x equals c. And our smallest value, if I'm seeing this correctly, appears to occur at x equals d. So from here, that's all we really need. We can see where the highest and lowest values are. They both have a closed dot, meaning that they're defined for this particular function. So we can literally say our absolute max is at x equals c, and our absolute min is at x equals d. So cool. So your mind might start to think, well, that was easy. Isn't it just going to be the same thing every time? And the answer is no. So let's look at our next interval. So I'm going to try to use a different color here. So on the next interval, we're on the open interval from a to c. So we're basically going from here to here. So what that does is it immediately eliminates our ability to use x equals c's high point. So as far as other high points, you might be tempted to say, well, it's something really close to c, like c minus 0.1 or c minus 0.001. Unfortunately, we don't have the ability to state the closest value to c because there are an infinite number of real numbers in there. So in fact, for maximums in b, there are none. There isn't a maximum. We know it would be at c if it could exist, but unfortunately we can't say that because c isn't included in our function. And on the flip side, you might say, well, there's no minimum either because d's not in there. But look at our graph. For part b, the lowest value actually occurs at x equals b. So weird as that is to think, since we eliminated that other section where it went down further, we had a slightly higher option, but it was definitely the minimum for the interval we were looking at. Moving on to section C. We're on the closed interval from B to C. So B to C. So in looking here, since we're including B, we get to include this low point down at the bottom. So the absolute min is going to be at x equals b. We didn't get far enough over to the right to include the one at d. And the maximum obviously occurs at c for the whole function. So on this smaller subinterval, x equals c should be the maximum as well. Finally, I don't think I've used black in these videos. So finally, the last one is on the open interval from a to d. So in looking from a to d, obviously we just lost our absolute minimum at d, and there are values in between the other one we had on the smaller interval, or smaller subinterval. So our absolute minimum is none. We needed to include d to allow for that. The absolute maximum, though, once again, we've included c in our interval, which means that the absolute maximum occurs at x equals c. So in this case, there's nothing particularly fancy about the work you're doing. And again, there's justification I'm sure you could go through. We're really just looking at it and trying to use our visualization and what we know about the intervals to analyze the function and find where the maxes and mins occur. And typically this has been like a short kind of multiple choice-y kind of question on exams, usually like a 1, 2, 3 type thing. Okay, that brings us to questions later on the text or the assignment. This one is from the calculator active portion, so I should probably include this in here, TI-Smartview. So we'll let that pop up here. It says in question 14 that the function f has derivative f prime of x equals this mess, and then it wants us to find any critical numbers of f on -1 to 10. So we're interested in the interval from -1 to 10. So now there are a couple different things that could happen here. Let's go no purchase. Oh no, I can't purchase that yet. We'll do no for now. Maybe someone will gift me this program so I can continue using it later. Okay, so we're interested in what's happening with this function. Let's give it a shot. So we have sine of x. We have ln of x plus 1. And then we have -4 over x. And I don't really know what the zoom's going to look like, so I'll just go zoom standard to start. Okay, so that's interesting. So looking at our picture of, a couple things to point out here, by the way. This isn't our function f. We're looking at the derivative here, by the way. So we're looking at the derivative. So remember, we're looking for where f prime of x equals 0 or undefined. While f of x, of course, exists. So I probably should have said c. So let me c right to that. Boom. So with that in mind, that's what we're looking to prove here. So looking at our picture, we can see that, okay, we're looking for places where the derivative is 0. That means we're going to look for the spot right there and right there. And then you might be tempted for a second to think about x equals 0 as well. Because, of course, x equals 0 does cause our derivative to be undefined. If you plug it in, you get 0 times 0 minus 4 over 0. And, of course, there'd be a problem. So let's address that issue first. So at x equals 0, f prime of 0 is undefined, or in particular at x equals 0, f prime of x is undefined. But in this case, we can't include x equals 0 as a critical number, and it's a little bit harder to convince you, especially right now, because we don't know what function has this particular derivative. But I'll let you know right now that the function that has this derivative, consider this like a special preview, the function that has that portion of the derivative, f is equal to stuff minus 4 natural log of x, absolute value of x. So just as a heads up, you're getting a super preview of this because of the way I wrote the question. So if you take the derivative of negative 4 ln of absolute value of x, you do get negative 4 over x. And what that tells us, of course, if you plug 0 into that function, you get negative 4 ln of 0, which is undefined. So basically, not critical number. And again, I probably shouldn't have spoiled that for you, but hey, you got a head start on the first day of term 3. Whatever. So that's our first option. The other two options we need to actually find on the calculator. So in looking here, I'm having trouble seeing them, so I'm going to go ahead and shrink this down a little bit. I'm going to first go from negative 1 to 10, just to make sure it's visible. And then since we're not interested on that left value, we're going to go from negative 5 to 5, just to make it a little easier to see. Okay, so we can see right there, critical number, critical number. So let's go second trace and find them. I'm going to use the 0 feature this time. Go ahead and start there. We've got 1, 2, 3, 4, 5, 6, 7. So go from there to 7. I'll guess 6. So our first one is 6.587. So that's 1. So these are, of course, the places where f prime of x equals 0. And so it's implying that we have our two values. There's our first one. To get our second one, we'll do the exact same thing. We'll do our 0. We'll go from there to 9.9. And we'll just guess somewhere closer. 9.238. So again, we used our calculator. We found our little intersection. In fact, let me copy this really fast just so that we have it in our picture. It's always good to get that. So there are our values we found. And again, for our job, we were supposed to find the critical numbers. So those critical numbers are exactly the values we just found. And I'm going to be extremely savvy here and time-savvy because I'm hungry for lunch. Those are our two critical numbers. Okay, finally, this brings us to the last question on the assignment, question 15. But I'm not going to spend time going through questions A and B from 15 because I feel like they're just very clear to go through, particularly after working through the previous section using the graphing calculator. So instead, I've focused us in on question 15C and D. And we're going to start with question 15C. So in 15C, which of course provides us, this question itself, provides us a graph of G prime. So this is G prime of X, not G. We are told to find the critical numbers of G prime of X. That's what we're trying to figure out here. What are the critical numbers for the derivative? So following the definition, it would be worth asking yourself, well, isn't that just like saying, when does G double prime equal 0? And I'm not going to include undefined here because it looks like a polynomial, but setting that aside. Isn't that the same thing? And the answer is yes, but the problem is we don't have a picture of G double prime. We don't see what G double prime looks like. So we'd need something else a little bit more helpful for us to go there. We don't want to have to construct values, particularly in light of not having any y values specified here. So instead, it was a small theorem that we discussed really briefly in class, which said something to the effect of the critical numbers are, what do you call it, relative extrema, or local extrema, always occur at critical points, right, critical values. So in other words, looking up here, since we're looking for the critical numbers of G prime, we know that they will occur anywhere where there is a relative extrema. So in other words, there's one right here, there's one right here, there's one right here, and there's one right here. Specifically, if we want G prime critical numbers, those critical numbers are going to be x equals 2, 4, 5, and 7. So again, this takes a little bit of thinking about, but here's another way that you might be able, maybe this would help you figure it out a little bit more, figure out why. If we're interested in G double prime of x is equal to the derivative with respect to x of G prime of x, right? Would you agree with that? Yeah, I agree too. So that's the same thing as saying the slope of G prime. So now, of course, what we were interested in specifically is figuring out when does this equal 0, correct? So what we're asking is when does the slope of G prime, so I'll put in parentheses so it's clear, when does that equal 0? Well, the slope would be 0 anywhere we're at a high point or a low point because of the fact that if you drew the tangent lines there, they would be flat. They'd be horizontal because they have slope m equals 0. So if you needed another way to kind of help explain or visualize why it is that it works out that way, there's a good one for you. And last but not least, 15D. Is g of x a continuous function? You know that function g that we have so much information about. Explain your reasoning. So the question here is, it's a tough one. I came up with this one last night as well. I thought this was a really neat question to test your understanding of some topics from the last unit. But we have to think about what we know. So is g a continuous function? Well, the question is, what are we given? Well, given good health, we're given, a thumbs up at some point. Maybe we might feel good. Given a sheet of paper with problems on it, good instruction and videos and stuff. But more importantly and specific to this problem, what we're given is literally the graph of g prime. We can see what g prime of x looks like. So here's the question. If we basically know something about g prime of x, yeah, I agree. We do. So now, what we need to figure out is, well, does that tell us anything about the information about the function g? Well, what I notice is that the graph of g of x, it exists everywhere. There's no issues, there's no jumps, there's no holes, there's no asymptotes. And we can assume because of the arrows that this function behaves the same way here, that we have a representative picture of the function. What that tells me is that visually speaking, it appears that g of x, prime of x is continuous. So in fact, this will be my little proof here. G prime of x is continuous, based on the picture, of course. If that's true, g is differentiable, right? I mean, that's just the definition of differentiable that we've mentioned before. If the derivative is a continuous function, then we'd say that the function itself is differentiable. Finally, the last piece that we want to look at is, of course, if g is differentiable, thus g is continuous. Because we've mentioned before, differentiability implies continuity. You can't have a derivative without having the function there. So in other words, with that in mind, we were able to prove it. If you're looking for kind of the explanation and answer, there it is. So again, just kind of an interesting one. This is very mathematical. I mean, if you're one of those people who thinks you might be interested in studying math, this is the kind of question that kind of gets towards the heart of what it's like to actually study advanced mathematics and abstract mathematics. You're using properties and axioms and definitions to explain your way through things, in addition to, of course, the typical problem solving that you do anyway. Without further ado, unless there's something after it, yes, there's not. Thank you for watching. Hopefully this has been informative and helped get you off to a good start in this new unit. Have a good night.